Hi, I'm John Soltis, and today I'm going to be presenting on some work I did with some collaborators last year, focused on predicting follow-up observations of galaxy clusters using machine learning. So, galaxy clusters, as many of you may know, are the most massive gravitationally bound objects in the universe. Because they're the high-density peaks of the mass distribution of the universe, they're a useful probe both of dark matter physics and of cosmology more generally. But they have some active, outstanding questions in their research that would benefit from better observations and more observations. And two important ones are characterizing and understanding the sources of mass estimation bias and better understanding the core cooling physics of clusters. So, focusing on the first of these outstanding questions, mass estimation bias. One of the ways that galaxy clusters are useful for constraining cosmology is by counting their mass, or counting the number of clusters as a function of mass, or the mass abundance. But obviously mass is not something that's directly observable, so you need to construct some sort of mass proxy. A way to get low scatter mass proxies is using X-ray observations. Unfortunately, we know that these mass proxies are biased, and we have reason to believe that the bias is related to the dynamical state of the cluster. So how churned up, how turbulent the cluster is, how disturbed the cluster is, probably from its mass accretion history. For the second issue, we know that galaxy clusters have different behaviors in their core. There are some galaxy clusters that have what we observe to be cores with a very short, relative to the lifespan of or a relatively short cooling time, and yet when we observe them closer, it doesn't match our expectations. And so we think that there's some heating source that's preventing these cores from cooling in the way that we might expect, but better observations and more observations would be useful in constraining that. So what's our motivation for doing this work now? eROSITA is an X-ray instrument that's currently in the sky observing galaxy clusters. And is expected to observe many more galaxy clusters in the X-ray than we have so far. However, to address these outstanding questions, we would like to have higher spatial resolution and longer duration time observations of these clusters that eROSITA will observe. So we would like to be able to do follow-up observations with instruments like Chandra. Unfortunately, follow-up is time-consuming and expensive, so we can't just do this for all of the clusters that we're going to observe with eROSITA. So we need some way of evaluating which clusters most merit being followed up with some other instrument. So we need to construct a follow-up merit assessment tool. So what we want this tool to do is we want it to be able to predict what a follow-up observation is going to look like given some existing eROSITA observation. And we want that follow-up observation to focus especially on preserving properties that we think are important about the cluster. And this important property that we're most concerned with in this paper is the morphology of the galaxy cluster. And that's because morphology is correlated to dynamical state, which, as I've mentioned, is important in understanding this mass estimation bias. Morphology is also related to core type, which is another one of these outstanding issues that we want to have a better understanding of. And morphology can also be correlated to the mass of the cluster itself. So we break down cluster morphology into three key simple parameters: concentration, asymmetry, and smoothness. So concentration is, as the name suggests, just a proxy for the how concentrated the galaxy cluster's mass distribution is. And the way that we construct it is we take the ratio of the flux within 10% of the R500C radius of the cluster and divide it by the flux in the image within the full R500C radius. And so just to give you sort of a quick visualization of that, you can imagine this larger circle being the R500C radius of the cluster, which we're just using as a measure of the extent of the cluster itself. We're saying this is the full size of the cluster, and then this is this 10% of that radius. And we're saying that that's the core of the cluster. And so the ratio gives us a sense of how centrally concentrated the cluster is. Asymmetry is just the absolute difference between the cluster and a 100-degree or 180-degree rotation of the cluster, again, normalized by the total flux. And smoothness is just the absolute difference between the cluster and a smooth version of the cluster. And so smoothness obviously is a way of trying to look at the clumpiness of the cluster, which again is going to be related to the dynamical state and other properties that we think are important. So to train a machine learning algorithm, because again, we want to make this tool as a deep learning model. So to train a deep learning model, we need a lot of data. So we use galaxy clusters that are simulated by the cosmological simulation magneticum, the hydrodynamic cosmological simulation. We end up with around 3,000 clusters with a variety of masses and redshifts. And we construct mock observations of these clusters using the Fox algorithm. For these observations, we incorporate a 10 megaparsec depth around the observation or around the cluster that we're looking at to get some of the local environment. And we also, when constructing them into images, try to have an eROSITA-like resolution. The images have 3 X-ray bands, the soft, medium, and hard. And we construct 2 types of images, 2 kilosecond observations and 10 kilosecond observations. So these 2 kilosecond observations, we then apply through the 60 software, which adds instrument response and background and makes them eROSITA-like. And so we're going to use these as the inputs to our model. And then we have a 10 kilosecond observation, which we do not add any instrument response or background to. And we treat this as an analog to a follow-up observation. So this is the idealized observation. So for the model itself, we use something called a convolutional neural network. So a convolutional neural network, as opposed to a more traditional dense neural network, has the advantage of preserving spatial relationships of pixels, which allows it to learn from images faster and also to learn patterns in images with less data. So if you want to get a sense of how these work, there's an example to your right in this nice GIF. You can imagine that this matrix here to the left is say, the inputs to some model. And then the model itself is just a series of these kernel matrices. And the way that it produces a prediction is it slides these kernel matrices across here, multiplying and summing up the values and producing a new image. And so what these kernel matrices do is they effectively look for patterns in the image. And during training, these weights are randomly set and trained over time to figure out which patterns are the most important. So we keep that thought in mind when we constructed our model, because we were interested in different length scales, especially preserving the fidelity of small length scales in our images. And so we probe a bunch of small length scales simultaneously. So we don't just use this like 3x3 shape that you see here, but we also do a 5x5 shape and 1x1, which when you have a 3-band image is effectively probing the spectral information of a single pixel. So how do we train these algorithm, or how do we train this model? We put inputs in, which are again these eROSITA-like observations, these 2 kilosecond observations of the cluster with background and instrument response into the model. It produces a prediction that is trying to match what we say is the truth, which is the idealized observations that don't have background, that don't have instrument response, and that are 10 kiloseconds in observing time. And we compare the output of the model generated from this input to the truth. And then based on some loss function that we try to minimize, the weights of the model are changed, and ideally the prediction starts to approach the truth. So for our specific case, we use a special loss function that we call the morphology loss that compares not only the difference between the individual pixel values, so this is just saying the mean absolute error, so the mean absolute difference between the fluxes in the individual pixels of the prediction image and this truth image, but also looks at what we call the fixed morphology mean absolute error. So what's the fixed morphology? So it's the morphology parameters again, but because we're doing this during training and we don't want to give the model any information about the mass of the cluster or the true extent of the cluster, we don't give it any R500C information like we do when we're evaluating. And instead, we use fixed morphology, where the fixed is talking about how it's fixed in pixel space. So for the concentration, for example, the ratio is now between the flux within a 10 pixel radius of the center divided by 100 pixel radius of the center, and the asymmetry and smoothness are defined over the entire image, not just over where we think the cluster is. Okay, so how do we look at the results then? I think it's important to break down the different kinds of images that we're working with. So we have, again, the truth images, which are these idealized 10 kilosecond observations. We have what we call the eROSITA images, which are these 2 kilosecond observations with instrument response and background. We have the eROSITA NR, which are background subtracted versions of the eROSITA images. And we use these as a sort of a simple non-ML comparison for our model. So just if you were trying to create a merit assessment tool, but you didn't want to use ML, so what's the sort of the simplest thing you could do? You could just subtract the noise and then see if what you produce is faithful to the true cluster morphology. And then the final image type that we're using is the outputs of the models themselves. And so one of the ways that we're going to evaluate the effectiveness of our model is we're going to look at how well the images produced by the model, right? Because the model is just producing images. How well the images produced by the model faithfully preserve the morphology of the cluster. And so the way that we check that is we calculate these morphology parameters off of the prediction image and compare them to the morphology parameters calculated off of the truth image. And the way that we, compare it in a relative sense to see how well it's doing is then to also look at how well the morphology parameters calculated off of the unimproved eROSITA images compare to the truth, and how the morphology parameters calculated from the noise or the background subtracted eROSITA images compare to the truth. So just as an example of what these images look like, so in the rows here, you're seeing the different frequency bands, and in the columns, you're seeing different observation types. So on the far left here, you're looking at these eROSITA-like input images. These are the images that go into the model. In the center left, you're looking at the background subtracted versions of these eROSITA-like images. To the center right, you're seeing the CNN predictions. So these are what the model outputs. So if you put this into our model, this is what it gives you. And then to the far right, you're looking at what we consider to be the truth. So this is what the model is sort of trained to try and predict. And these are these idealized 10 kilosecond observations. So looking at the parameters, so again, these are parameters. This is concentration as calculated off of images. So blue is talking about the concentrations calculated off of the unimproved eROSITA-like images. Red is talking about the concentrations calculated off of the background subtracted eROSITA-like images. And green is talking about the concentrations calculated off of the prediction images, off of the model outputs. And we're looking at an error here. So it's the concentration, say, calculated off of the prediction images, subtracted by the concentration calculated off of the truth image, off of this rightmost column. So what you see here is that the dots correspond to the median error, and the colored in region corresponds to where 68% of the error falls. And you can see right away that the predictions from the model are more morphologically accurate and more precise in their accuracy than the unimproved eROSITA-like images or the background subtracted eROSITA images. So that's good. That means that the model is working. That means that it's producing images better than we could get without using the model or without using some simple alternative. This pattern is repeated for the different bands that we're using, which is also good. And on the bottom here, I'm just showing the true distribution of concentrations for the clusters. So this gives you a sense of the size of the bins for these different error bars here, and also what the distribution looks like. And so this pattern is repeated for these different morphology parameters that we're interested in. Again, you can see that the asymmetries of the images produced by the model are more precise and more accurate than the asymmetries from the unimproved image or from the background subtracted image. And we can see again that this continues to hold true for higher energies. And the same is especially true for smoothness. You can see that the unimproved image and the background subtracted image have a strong bias relative to the prediction images, which correct for that. And the prediction images also have a narrower band of error. So what we're seeing here is that our model achieves what we want it to. It's producing morphologically accurate images of what a follow-up observation would look like based on how we're defining sort of a follow-up observation, which is this truth image. But before we apply this model to real data, there's some questions that we want to think about. So our model is being trained on simulated data. So it's simulated galaxy clusters and it's simulated observations of those galaxy clusters. But those simulated observations and those simulated galaxy clusters are going to differ from real data, from real galaxy clusters and real observations in important ways. And because the model is trained on simulated data, its predictions when applied to real data is going to be biased. And this is something known as domain shift. But there's a potential way of mitigating this problem, and that's by using something called transfer learning. So essentially, we can train on simulated data and on simulated observations of simulated clusters. And then we can fine-tune train the model on pairs of real observations of clusters. So say if we have a bunch of real cluster observations from eROSITA, and then we have archival or follow-up observations of those clusters with some other telescope, we can try and make our model more robust to domain shift. And this is something that we're looking to do in the future. Okay, so in summary, we can say that galaxy clusters are important probes of cosmology and good laboratories for astrophysics. They have some outstanding questions that would improve their power as a probe of cosmology and laboratory of astrophysics. And those questions are about galaxy cluster dynamical state, they're about mass estimation bias, and they're about the core cooling physics of galaxy clusters. And follow-up observations that have higher spatial resolution and longer observing time would be useful for resolving these questions, but unfortunately, they're expensive and time-intensive. But luckily, we've shown that deep learning can help solve this problem because a deep learning model can produce morphologically accurate and precise long-duration background-free galaxy cluster observations given some eROSITA-like observation. So this model can output images that can usefully describe the clusters and can help observers decide whether or not they think that the cluster is morphologically interesting enough to merit follow-up. There's continued work that we would like to do before we apply it to real data, but I think that we've shown sort of that the premise is possible and that this is worth continuing to work on. Thank you.